All right, good afternoon, everyone, and welcome to today's webinar, A General Introduction to the Semantic Web. Before we begin, a quick reminder that this session is being recorded and will be shared through our dissemination channels, YouTube, social media, and websites. We are very pleased to have with us Dr. Andra Waagmeester. Andra is an assistant professor at Amsterdam University Medical Center, specializing in semantic web technologies, knowledge graphs, and biomedical data integration, with a strong track record of publications and contributions to open science. His work focuses on making scientific data more structured, interoperable, and reusable, helping advance how knowledge is shared and connected across the life sciences. Thank you all for joining us. And again, thank you, Andra, for accepting the invitation. And the floor is yours.
Thank you, Soderwilla. Thank you for the nice introduction. I'm really honored to be here, and I would like to give today a gentle introduction to the semantic web. And I try to keep it as gentle as possible, but in the end, I permitted myself to do a bit of a deep dive. But what I would really like to introduce today is what is the semantic web and where are we using it. The short version is the semantic web is an extension of the World Wide Web. We all know when we browse. And when the World Wide Web was envisioned about 20 years ago, a bit longer, and it was primarily about documents. And what is semantic about it, it's the same principles, it's the same way of working, but then it's on data. So maybe I want to start with a short story, which has been the red line in my whole career so far. Is when I started working, I had two colleagues who were specifically hired to build a relational database for a collection of Excel sheets, because at that time in that department everything was Excel. And they worked for, I think, 2 to 3 years to finish a completely relational database structure to keep the same data, but structurize it into the relational database and have the constraints and the validation that comes with relational databases. And the irony is when they presented their work, and they got one of the leaders then came to them and said, "This is really, really nice work, but can you convert it back to Excel?" Upon which to actually quit, because but why I'm saying this is because the Excel remains the primary core of data sets to this day. We have relational database, it's the most universal data format in the world, and it basically offers two things: structure and flexibility. And it's still, even after those years, one of the primary captures of data in our day-to-day work. But there is one problem, and that our world doesn't fit in a two-dimensional pane. It has many dimensions. Tables have simply two. And the world needs to express a time. When did this happen? For how long? What is the sequence? Who added the data? What is the relationships between the Excel sheets? And how confident are we about the values in there? If we see that some value is not stored in a cell, does that mean it doesn't exist? Does it mean it hasn't been recorded? Or is it some other omission? And then we also need context. And what we're basically trying to do is with data is trying to understand our data. So if we have a reality, if we try to capture our reality in a set of two-dimensional panes, and if we store those in tables, we then try to reconstruct or build a model of the data collected in a set of Excel sheets, we end up with a coarse reconstruction, and details are being lost because a lot of the context is also missing when we store the data in there. So ever since we start structuring the data, and more formats have entered the equations, and from the 1970s to the 1990s, we saw the immersion of tables, SQL, schemas, and single format, single vendor of relational databases. And in the 1990s and the early 2000s, we started seeing the emergence of file exchange formats. We have CSV, TSV for portability, where the data frame format of Excel sheets is being kept. We have XML for hierarchical data and EDI for transaction data, and basically each domain invent its own. In the 2000s and 2010s, we see the emergence of API and HTML with microdata, domain-specific schemas, and in the 2010s to until now, we see the emergence of specialist formats, FireOwl, Parquet, and I will dive into a bit of these later. But then with all these formats emerging from the simplified version I gave of everything is a table, we are now we have many sources, many silos, and trying to collect all and combine both is a very daunting task, if not at all, if at all possible. So the ambiguity problem is when we try to create the table, if we go back to the initial table, I see here we have the same table from slide 2, the patient ID, date, diagnosis, value, and units. So if you look at the patient ID, which system issues the ID? Is patient ID 123 in hospital A the same person as patient in hospital B? Is it a national number? Is it a system? Is it a number given by the electronic healthcare record system? The date, what is the date about? Is it about measurement? Is it about date of diagnosis? Is it when the lab was processing the data? With the diagnosis, what is the coding system? ICD-10, SNOMED, free text. Another issue that sometimes emerges is that we can edit data or typos, and that makes it difficult to connect. Values without a unit is meaningless, and the unit is we sometimes need to know the background of what standards are being used for the unit. And when we talk about units in this example, is it a standardized code, UCUM, or is it just free text? And again, how sure are we that there is not an error in the wording? So that was creating the complexity of the data integration that we're facing these days. And I'm here to say the semantic web will face it all. That's of course not true, but it will really ease it can, in my opinion, can ease our life quite a lot. Because and I will dive into that a bit later, while it's being perceived as difficult, in my opinion, it's actually quite trivial and straightforward. Because what we'll do with the semantic web, which again is a extension of the World Wide Web, is the first thing is everything we talk about will get an identifier or a unified resource identifier. Here I have instead of talking about diabetes, we're talking about SNOMED info and the SNOMED code. And then there is no disambiguity of what we understand with that number. And so everything becomes a number, and the disambiguation and the ambiguity of the terms is fixed. And then the other quite important thing happening when data is being published on the semantic web is that everything is described into a triple, what's called a triple or a sentence. So whenever you import Excel sheets or XML data, you can have as many values as you like. With RDF triples, which is the basis of the semantic web, that's not the case. All the data is being expressed in those triples, and which is the subject. So in this line here, we have the patient 1234 has diagnosis SNOMED 732110009. And then the third thing is, because we start using identifiers that follow the same pattern as a World Wide Web address, we can start linking data sets without having to integrate them together. So a patient has a gene, goes to a protein is part of a pathway. All these elements can be from different data sets, but because they use the identifiers, we can basically go from one to the other, and we no longer need ETL pipelines to get from one to the other. So Tim Berners-Lee is the same who envisioned the World Wide Web as one of the three, also envisioned the Semantic Web, and I think it's in 2010 came up with the following 5-star linked data, how to transition from your data to be to a fully accessible on the Semantic Web. So and there is a link down there which I recommend to follow, which clearly explains which steps to follow. But the first star is it is about adding stars to your data. So you can add 1 star to your data if it's accessible via web technology. And one caveat I would like to make here. This does not need to mean that the data needs to be accessible to the world. It just needs to be accessible with web technology. And so your data can already be 1 star if it's just a digitized image of a handwritten note. And there is a license that explicitly states whether the person, under what conditions the data can be used. So achieving a single star in this star scheme is pretty doable. The next 2 star is data in a structured format such as Excel or a proprietary database dump. It has structure. So from 1 star to the 2 star, we introduce structure. And if it has structure and the license, you have achieved 2-star data in the linked data network. The 3 star is a non-proprietary. The difference between the second and the 2 and the 3 stars is that with 2 stars, data that requires specific software to be used is eligible for the 2-star. However, if the data can be imported, ingested, or used by any software, then we have 3 stars. So the 1, 2, 3 star is the common data models we have been using. So moving to the semantic web happens in the 4-star and the 5-star. So as I said, when you use URI as identifiers, each concept gets a unique globally resolvable URI, and ambiguity disappears. If your data uses these identifiers and uses triples, you have 4-star data. The step to 5-star data is when you start using other people's identifiers. We can imagine that if we all start inventing our own identifiers, even if we express them as URIs, if others don't use our URIs, then we are still stuck in data silos. So this is a guideline, and the interesting part was the specification of the 5-star was published as a coffee mug. So everybody who was at the time wanted to read the specification could just buy or acquire this mug and had then the specifications of the 5-star linked data. So reiterating the RDF, that's the foundation of the semantic web. And every data speaks this. So we have a lot of formats. So what does the RDF solve? It solves format fragmentation. Every data source speaks its own language, and we move it to the subject predicate object format. One other thing is this is also different to storing data in a table, because the subject predicate object reflects how we speak in the subject verb object word order. So I would like to sometimes argue that this is more intuitive to work with data than we work with tables, because when we communicate, we don't talk in tables, we talk in sentences. And so the triple is the closest we can get to the way we talk as humans. And so to me, that is quite an intuitive way of how to store your data. And the second term is it solves the ambiguity in meaning. We don't talk about the words. We're all familiar with names that every language has their own. In Dutch, it's Jan. Many people's name is Jan. There are many Jan Janssens. So if you type in a Jan Janssen, there will be many people with that name. If you start using their LinkedIn profile as the web address, you suddenly have disambiguated the person, and the same goes for objects. So the RDF, which is the foundation of the semantic web, is just these two steps. Talk in triples and identify everything with global unique identifiers. And this is what I have. Oh yes, one thing is there is a third thing which is the namespace. So I've already said you can use SNOMED identifiers. So the namespace is, and I will come back to that later, is the basis of a set of identifiers. So as we've seen in the previous slide, we have here diabetes, we have the patient, and we have a LOINC code. So this is the namespace of this LOINC code. So now we know that this identifier belongs to the LOINC code. This patient identifier belongs to the Amsterdam UMC, and this SNOMED ID belongs, this identifier is a SNOMED term. But this is the, so the identifiers is, so when we start going to the 5-star, this is where we dive into the existing namespaces to identify existing Euro identifiers instead of inventing our own. So, and the namespace choice determines the granularity of your description. And that is sometimes overseen when we start, because and I'm the culprit of this as well, when I say we should really start using identifiers, I suggest using any identifiers. And the moment you have a URI, the work is done. But that's not completely true, because if you look for diabetes, some namespaces have a single identifier for both diabetes 1 and 2. So the clustering behind that code is also important. So choosing the namespace, whether it's ICD-10, MASH, SNOMED, or Chebby UniProt, there are hundreds, if not thousands, of namespaces, is also quite important before you start minting the URIs that you want to use in your data set. There are mechanisms to map one from one to the other, which I will dive into a bit later. In the design stage, it's good to understand what the granularity is of the data that you would like to cover. And a few years ago, I was in a heavy debate with someone who said that genes and variants are identical. So when you say something is a genetic variant, and another data point was annotated as it's a gene, then in that set of reasoning, it was suggested that the gene and the variant were the same. I said, but that's not true, because a variant is a specialization of the term gene. And his reply was like, no, I'm coming in our namespace, which was schema.org. We are not so much interested in the details, we're interested in findability. And if you're interested in that gene, you're also interested in that variant, which I think is a valid claim that disqualifies the use of that namespace for the use case, because you lose the granularity when you want to distinguish. So if you have a namespace that says a gene and a variant is the same, then you will not be able to disambiguate the two afterwards. So this is not a gentle introduction anymore, but I would really like to dive in here because the selection of the namespaces sometimes called ontologies or terminologies, is important when you dive into the semantic web. So the query language for the semantic web is Sparkle, and it follows the same pattern as in RDF, and it also, as I say, speaks English. English puts words in subject, verb, object, and Sparkle puts data in subject, predicate, object order. And once you've seen that, it's going to be pretty straightforward to write any query. So in this query, we want to know all proteins on the cell membrane that are associated with asthma. So the question is, the gene is associated with asthma, the gene encodes for a protein, and the protein is located in the cell membrane. And that reflects to these identifiers. And what is different, what is in Sparkle is this question mark gene. This will result in a table with all the genes that that encodes for a protein that's on the cell membrane. And this is by far my favorite quote. This is by Dan Brickley and Libby Miller. Dan Brickley runs schema.org, and he says, people think RDF is a pain because it's complicated. The truth is even worse. RDF is painfully simplistic, but it allows you to work with real-world data and problems that are horribly complicated. While you can avoid RDF, it's harder to avoid complicated data and complicated computer problems. RDF brings together data across application boundaries and poses no discipline or mandatory or expected structure. So again, as I said in the beginning, it is very simple. But with the simple, it becomes a messenger of how complex our world is, because then suddenly we have to represent our complex world with the set of sentences. Referring back to the image that I gave for the bird that was converted to a set of small, only collected in tables, you get a coarse-grained data representation of that set. Oh yes, forgot one thing. Next to Sparkle, we also have OWL. OWL allows you to formally reason over the data. So what you do in an auto set, you define hierarchy formats, and you can actually say that, and again in triples, hypertension is a subclass of cardiovascular disease, diabetes is a subclass of metabolic disease. And then once you do this, the patient with hypertension is automatically a cardiovascular patient. This can really be helpful when you start writing Sparkle queries on RDF datasets. So assume that you have a set of patients of which you have annotated that the patient has type 2 diabetes. You can use the ontologies behind that to extract all metabolic disease patients. So in your RDF, you don't have to say that the patient has a metabolic disease. The fact that you have annotated the database and you use the ontological knowledge in there, which will allow you to aggregate the information in the data. You can also say property restriction, constrain what is allowed, has parent, has a max cardinality 2, and has diagnosis must have some values from diseases. So again, you can use this reasoning, these types of reasoning to identify issues in your data. This one is specifically interesting, and I will come back to that later, because an ontology will describe the reality. In our biological world, a child has two parents. But if you go to the data and you run this ontological constraint validation on the data, you might run into issues that will validate the data as incorrect. Whereas in the data, in a lot of the cases, a parent is not limited to only biological parents. You have caretakers, you have somebody who has some custodial relationship over the child, will be annotated in the data as having a parental reason. So then the question becomes, do we adapt the ontologies? Or will we have a different set of constraint violations for the data where we say, yes, a child has a custodial and a custodial relationship with person if the person is a parent or a teacher, and so that is something, and I will discuss it in a bit. That is where we talk about data shapes, but I want to make this point, and I'm aware that I'm already going behind the gentle introduction, but I want to make that clear. So when we do OWL validation on RDF, it's on knowledge. So an ontology represents the reality of life. The data shapes which I will introduce later is about the data that represents, and I'm going to repeat that when I talk about data shapes. And finally, we can also address equivalence. So SNOMED SNOMED. This number is the same as ICD-10 E11 and alive is not this cannot be this at the same time as diseased. So when you write these triples, the reasoner derives that the patient has a cardiovascular disease, because we don't say that the patient has hypertension, but that is inferred from this line. And here it says the contradiction is the patient 42 is both alive and deceased. So I have gone on to RDF, Sparkle. So RDF is expressing your data in sentences using identifiers. We store this in long lists of triples, which we call RDF. We query them with Sparkle queries, where we deploy ontologies to get inference out of. So I have already said it's pretty easy and straightforward to write Sparkle queries, but finding your way through the identifiers can be very complex and can be intimidating, which is also why many perceive RDF as being complex. We are now having LLMs on the horizon, and I must say I have been exploring and exploiting the use of large language models in the generation of LLMs, and we are pretty much getting to the extent that we can actually start talking Sparkle to we can start natural language to those knowledge graphs that we have, with one big caveat that everything is still in its infancy. And here I have put in one, which is the LLM for query translator. This is specifically generated by the team of the Swiss Bioinformatics Institute that runs on their data set, and it gets some really interesting results, with the caveat that they learned their LLM on their data sets. So that is when I dived into ChatGPT or Claude, and I'm getting sensible Spark queries out there, but I lost also quite substantial amount of time because Petros said you don't see my slides?
No, we do. At some point, it becomes a little bit blurry, but it comes back.
Okay, and I will share the link here. It's online, and I am now at slide 16.
Thank you.
So there are many issues with well, I mean, I'm saying LLMs. I'm really diving in, and I recommend everybody. It is also a nice way to learn, but there are quite some caveats. And the thing where I lost most time is this issue, which is not limited to the LLMs as well. Is this difference between HTTP and HTTPS, and so and it's actually what I tried to put in these lines. I said when using LLMs generating queries, verify the prefix declaration first. This is something one should do by design, whether you use LLMs or not, because one of the usage of the ontologies is a living system. So when schema.org initially started using schema.org, they minted everything as HTTP schema.org and the name. But then the HTTPS entered the equation, and people started using HTTPS. It's the same URI, but one is HTTP and the other is HTTPS. And there is a mix of opinions in there. If I move to Wikidata, there is and I can try doing this, there is the address, and this is the URI version of a Wikidata item, which is, please do note, HTTP and entity. And when we click on that, it transfers automatically to the HTTPS, and it has a different name, wiki, because this is the human version. But if I go to the and I need to cheat a bit. If I go, I cannot change this here, then I will do it quickly here. If I go to 42.ttl. Yes, this is Q22. You will get the way the machine see it. So going back to the slide, there is a difference between the entity URI and the page URL, the HTTPS. This points to the human readable version, and this points to the machine readable version. But if you're in a browser, clicking on the entity, it will automatically go to the human readable version. So why is that? Why is that causing issues? Because if you're a data curator and you're looking to Wikidata and it says, yes, I'm interested in Q42, then some will use this as a URI, whereas others will use this. So you haven't. So the name, again, this is the namespace is being used. And the same goes for schema.org. So when I think this happened 7 or 8 years ago, that they moved from HTTP to HTTPS. And that will cause a lot of confusions. And for me, this has been the biggest issue when I use a LLM based Sparkle query, because the LLM will normalize that and will give you only a subset of it. So if you get a query that is LLM generated, and they picked, for example, the first HTTP but put in and ignore this, or vice versa, you will get a query that doesn't work. Whereas the full structure of the query works is the selection of the prefix. I'm not saying this is the only case, but I just wanted to point out that when you use LLM, these are the things that can lose a lot of time in working. So in the details section on the presentation, there are more examples given. So far, how am I in time?
We're doing good.
Okay.
We have another like 15 minutes or so.
Okay, so this is the basics about RDF, going into Sparkle, going into OWL, and then using LLMs to write Sparkle queries. Sparkle has an other interesting perspective is you can actually Sparkle as a web service. So if you I haven't have it clickable, but if you go, for example, to Wikidata, I still have it here. And I do just the first, and I'm taking this query and I run it, and I should never do a live version. I will take the cat one. This one is we'll get the results, but if we click to code, we see a whole set of programming languages that we can use and embed, and then we can start embedding the Sparkle queries that we have introduced in our lines, in our applications. So here I have one as a Jupyter notebook, and it is a Python script where you first say there is a Sparkle, this is the endpoint where it's coming, this is the query, and it will format it as JSON, and the JSON can then be picked up in the Jupyter notebook to do further analysis. So then you can actually write Sparkle queries that you can embed in your pipelines. And once the Sparkle query is written, you have set your ontologies, you have set your query, and then you can build your bioinformatics pipelines to assess the data. And only when the data schema changes, it is when you have to write a Sparkle query. So this also means that not everybody that will use this data needs to be familiarized itself with Sparkle. Where the Sparkle queries can be written by someone who is proficient in Sparkle queries. The Sparkle queries will result in JSON or table formats, and that can then be embedded in Python Jupyter notebooks of R studios. So now I've created this. Now I'm really doing a deep dive, and it's what I just said about data shape. So I already talked about ontologies. So an ontology is where you said if somebody is dead, they cannot be alive. A person has two biological parents or has parents. but the data can be a lot more fluid, if I may say it like that, than what the ontology says. So you might not want to use ontologies to verify your data, but you want to use data shapes to verify what is in the data. And in your shapes, you use ontological knowledge to verify what is in there. So in the example of the parental relationships in data, which can be a combination of custodial guidance and parents, that is what you reflect in a data shape. So there are three main languages now, which I'm not going to dive in now, the Shack, Shackle, and LinkML. I have some details on the slide down there for those who want to follow on the slide. But what it does is you write the shape expression, and this is a shape expression that they say the record must have a patient, it has ID, it has a minimum, there should be at least one, and a data type should be an XSD string. So if you write patient 1, 2, 3, 4, 5, when you use the data shapes, it will tell you that this is accurate. If the patient is question mark, question mark, question mark, it will violate that. So this, while RDF is just one big set of linked triples, using these data shapes allows you to validate the consistency of the data in your data set. And what does the shapes allow you to do more? First of all, it's also a way to document your design choices. So whenever I make a new RDF data set where when I make some choices about namespaces, about identifiers, about the structures that are being used in RDF, with structures, I mean set of triples that are reflecting a single fact, that can be documented using in the shape. The second thing is you can use the data shapes to see if existing data fits the expectations. It's not always that you start with a blank data set. Sometimes there is existing data sets, and when you write a shape, you basically write the expectations of what's in the data, and you can use those data shapes to check if those expectations are met. Another very handy application of this is sometimes when you check the data set, and you see that the data set is consistent. But after submitting the data into the system, you can basically check if there are errors and the inconsistency. Can you check for errors and inconsistencies? And finally, you can also check after updates. You can keep testing if the data, because data, especially in those RDF knowledge graphs, change over time. Also, a very interesting rule is whenever you do a validation of your semantic web data and you get an error, please don't think that the data is wrong. Because especially in the beginning, when you start working on using data shapes and RDF serialization, sometimes the data is accurate, but the data shape is inaccurate. So we constantly have to see, here is one example, has a birthday, some data sets write circa, and then it will be a violation. But this is actually correct. So then the question is, do you change that in the, we have done a data set where the requirement was that circa, because circa 1940 could also be 1945. So if that is the case, the data shape needs to be adapted to account for these values. And then let me see, one more point is where data shapes can be really helpful is, I already said we have ICD-10, SNOMED, and the granularity of the namespaces. With shapes, if you start describing those different, so you can have the same data set being represented by multiple namespaces. You can use the shapes to describe the data in the different data namespaces. So let's say you have 4 namespaces. You can have 4 data shapes that represent the same data. And then we can use the shape maps or these 4 patterns to go from one namespace to the other, with the caveat that I said in the beginning. if you start out with one data set and one namespace that is not granular enough, you will never get the granularity again. So the thing about RDF, once you have RDF, you can actually move from any namespace to the other as long as the granularity is accounted for in the beginning. But once it's there, it's not, you can change from one namespace to the other using these namespaces, and then using these data shapes. So this is an actual example where there has been where the shapes are being used to map between FHIR and OpenEHR and OMAP, which I'm going to skip over this for the sake of time. And one more thing I would like to see, because there is also ONTOP, and ONTOP is also some sort of data shape, but it's a bit different. Here you describe the data shape mapping to a SQL database or relational database. And by doing so, one can actually write a Spark query that will be reformulated. The Spark query will be reformulated by ONTOP to an SQL query that will be executed against to the relational database, which will return a Sparkle endpoint. So by using ONTOP, you can actually query relational database with the caveat that this can slow down your performance substantially, depending on the amount of joins you have to make. So if you say if two values in a triple are from six are linked through six tables in a relational database, that means that the joining of those tables has to happen over the querying. But it's something that we are now exploring into quite a lot, and because, as I said in the beginning, people still love Excel, and getting from Excel to RDF can be daunting. So having a middle ground as ONTOP can really help in this. And here I have an example by my colleague Rodi de Groot, who had OMOP data that he then converted using ONTOP to RDF and through RDF to FHIR. So showing in this example that from a relational database in OMOP, we can integrate into FHIR. So that I think wraps it up. And so I started out, we have raw data, tables, we have XML, JSON, then we have the semantic foundations, the triples, the namespaces, and a way to bridge between the namespaces and the IRIs. We have ontologies and shapes to infer over knowledge and data. And we have various ways. Oh, I didn't address, there is also a framework called Sparkle List, which allows to give you REST APIs from single Sparkle query that comes a bit on what I saw on the Jupyter notebook. And then through these, you can use our AI dashboards, federated analysis in there. So what we've covered, data has limits, the semantic offers a way out, shapes adds discipline, namespace choice is a design decision, bridging is possible, and virtual knowledge graph skips the ETL entirely. I've put in here some further reading what I can recommend, and I think that is it. Thank you for your time, and I'm happy to take questions.
Thank you very much, Andra. It was very interesting, the presentation. Do we have any questions? Maybe I should start with one until we have some hands up. So if you create data shapes, they can make mistakes. If you get
Yes.
an error, I guess you go back and you can check if it makes sense what it says. But if it comes out correct, but it can't. Well, my question is it possible that it shows that something is okay, but it's not, and it's not detecting it?
Yes, that's the short answer. But that's the same answer as with the other way around. So it's about, so the shapes eventually will be very straightforward and set in stone once you go to production. But especially in the design phase, when you start exploring or designing your data pipeline, and that is indeed the biggest challenge because it's a multi-axial decision So what is it, if it's the ontology that you used, is that correct? As the example with schema.org, is it fine-grained enough? Let's stick with that, where they said a gene and a variant is the same. And so you have a gene and you check if it's a variant, but the gene, so you expect that the gene will be validated as an error because, yeah, they are different. But if the namespace says, no, they are the same, then there will not be an error. So that really chimes into what I said earlier, that we need you want to have that you need to dive into the namespaces that you use. And one thing I didn't address in here is, so what do you do if you have chosen, for example, well, let's take one of the oboe ontologies, and you find out that the ontology is missing the granularity, or there is a disease that you care for is not being covered. So what do you do? So basically what you ideally want to do is you want to talk to the ontologies of your choice. So, or the namespace of your choice. Okay, then engage with those curators. Says, this is my use case. This is the data that I have, and I cannot do any pipeline because it's not covered by your ontology or your namespace. And then it depends on if they respond, which sometimes can take 4 months to a year, because sometimes those frequency cycles are pretty slow. Then what do you do? So what you then do is you can make your own ontology, which is actually a bit of a no-no, but at the same time, sometimes you cannot wait for the fine-grained ontologies to pick up. So what you then do is you use your own sort of custom ontology or custom data shape. And then the moment it's going to be adjusted, you put in a mapping rule. And then you say, this is my internal one. It should be the same as that. But now I dived into much into your questions. But the short answer to your question is yes. If depending on the data, it can say yes, it's correct, while it's not. But that's basically how you. Did I get your question correct?
Yes, it makes much more sense the way you explain it about the namespace. It really depends, as you mentioned during the webinar, on the namespace, really how it defines the ontology you're using. Petros has a question. Thank you, Andra, for the answer.
Presentation. Can you hear me?
Yes, I hear you. No, I don't.
Okay, now.
Petros, it goes on and off.
What about now?
Yeah.
Okay, I have a problem with my headphones. I need to change them. Okay, so my question is related to your previous comment about namespaces. So given that there is some challenge to link different namespaces, what is the best approach when you are in the design phase? Is it better to limit the number of namespace ontologies that you use to avoid, mapping challenges and things like that? Or is it better to identify the most accurate term in terms of definition and in this way increase maybe a lot the number of different namespaces that you use in your use case? Thank you.
I really like your question, and there is not a single answer. I would say, and I sometimes compare it to someone who starts writing papers to a journal. In which journal do you want to publish your paper to? At some point you have your subset of preferred journals, but in the beginning it's often you go out and try to, especially if you're new to the field, and try to identify which is the best journal. It is not a complete comparison, but yes, I like your question. And I would indeed say try. So basically there are three answers to that. One is, yes, be as broad as possible. But sometimes with this broad approach comes time, and we don't always have time. So because in the end, you have to consolidate. As I said in one of my final slides, consolidating is very easy technically in RDF. You can go from one triple to the other. There are mechanisms to do this. So that's a no-brainer. The complexity comes in making the decision in the transference, because when you say this identifier is SNOMED ID is the same as ICD-9, and you only do that based on the term, you can sometimes make misconceptions. One example is burnout. I don't know which one, but in one of the ontologies, burnout is considered a job-related work, and in the other, it's considered an anxiety disorder. So the subclasses behind that structure says something on the inference, and so when you try to use those ontologies, and you say, okay, now we've decided we go from SNOMED to Mondo or from Mondo to SNOMED, you need to be 100% sure that the background of that term is identical or not. So that is one thing, but that's part of the game, and that's also trying to understand the namespaces. So I would indeed say in the beginning, I myself as broad as possible. The second approach is to use Wikidata. Wikidata is the triple store for Wikipedia. So basically, if you have a term that doesn't exist in an ontology, you either check if it's in a Wikipedia in a Wikipedia article, or if it's in a Wikipedia article. And especially if you're multilingual, you can check the different Wikipedias. And once there is a description of that term in Wikipedia, you have a Wikidata ID, and you can use that term. And in those Wikidata ID terms, you can create mappings. So this helps in one way. It helps adding your knowledge to the public domain and create. And then once you have found a term, you can update the mapping in there, and it's immediately linked. That is the second approach. But I can talk about an hour about how you do this in Wikidata. That's the second approach. The first approach is, and that's the easiest, and I have done that many cases, and this is especially, I guess, in your case as well, when you work with rare diseases, it's more likely than unlikely that the disease will not be covered by the big ontologies. And then it can be really helpful to just make your own ontology. And then you can go two ways. You make your own ontology, and someone recently said ontology is like having children. You need to be responsible for it at least 18 years. I think that is kind of a nice rule of the thumb. So once you make your own ontology, you want it to be reused, so it basically becomes a burden. Now I'm saying that my children are a burden, which they aren't, but those are the three things that I would say in your design choice. Those are the three things. I hope I answered your question.
Yes, thank you.
Do we have another question from the participants? Can I ask a naive, perhaps, question? If we structure our data that way, will it help with AI to boost the explainability of the black box of AI at the end of the day, because it can create better relationships between the data that is processing?
Your answer is as good as mine. I have been told, yes, that is the case. I haven't seen, well, I have seen it in Wikidata, but this is before the AI hype. That I was in a previous project, I was quite active in Wikidata, and by adding disease relationships in Wikidata and other, suddenly it popped up in Google. So the search engines picked up on Wikidata, and I assume AI does as well, but I'm not an expert on AI. So my assumption is yes, but I don't know the inner workings. Maybe some AI experts here know that more. I've been told, and I like that, and being told that we feed with this RDF work and the semantic, we basically feed the AI models, but how accurate that is, I don't know.
All right, thank you. All right, it seems that we don't have any other questions. Thank you again, Andra, for this great webinar and for your time. And thank you everyone, to all the participants, for participating in this webinar. Once we have the recording on our YouTube channel, I will share the link in this chat, and then our websites as well. Thank you so much, Andra.
It was a pleasure. Thank you for having me.
Good afternoon, everyone.
Thank you. Bye-bye.